Hello, everyone. Thanks for coming. I'm from the University of Michigan. My name is Ashwin. My colleague Mark Salamango was supposed to join me, but he wasn't able to make it. So between the two of us, he's the prettier looking one. So unfortunately, you guys are stuck with me for the duration of this talk. Um, so as I said, I'm from the University of Michigan, but within that, I'm from the School of Medicine. And so what I try to do is data science in medicine. Basically, they've given me a couple of titles, HR titles at the university, but foundationally, what I am is a data scientist. My background is signal processing, image processing, and machine learning. And luckily, I've been able to apply these skill sets in the field of medicine for the last 10 years. And so, my aim here is to try and see if these kinds of skill sets, which are not traditionally used within the field of medicine, can help in some way or fashion. So within the School of Medicine, there are a variety of research centers. One of the core research centers that I really am focused on is called Michigan Center for Integrative Research in Critical Care, or MCIRC in short. So this research center basically is spawned off of the Department of Emergency Medicine. There are several cores to this research center. One of the cores happens to be data science. The main mission, the main ideology of this research center is to develop solutions for the critical care space. Critical care has its unique challenges and it's pretty wide, so this research center is focused on that. So you have several research centers like Cancer Center, Cardiovascular Center. This is the Critical Care Center. Now, when we say critical care, you might be wondering, what does that exactly mean? Is it just the ICU? Well, the fact of the matter is it's much broader than that. Critical care really begins at the site of the accident or the incident, and this is where caregivers start giving some sort of help to the patients. This is where they also have the least amount of information about the patients. The amount of data that's available for them is at its least. So they try and do their best at this point, as well as during transport to an ER or an ED. So emergency department receives the patient. This is when they have a little more information. They're able to gather more information, take a few tests, so on and so forth. But still, they're fairly clueless when it comes to having data-rich sort of knowledge that they can use during their caregiving process. But there's definitely a lot more resources. So at the site of the accident or during transport, the resources are also very strapped. So at this point, at least they have more resources to work with. That then transitions into the OR, operating theater, where they tend to have a lot more information. They also have the ability to gain a lot more data. They can take X-rays, CT scans, what have you. They also instrument the patient with a lot of measuring devices, and that gives them the ability to diagnose the patient much better and also see if their treatment is working. And finally, it's for the prolonged care, which is typically in an ICU for drastic cases. So this is where I would say is the most data-rich environment in any hospital. You have abundance of data, you have abundance of ability to collect data. These patients are typically instrumented with at least 10 different devices, which is constantly collecting data. This is in addition to when the nurses come in and start making notes and putting that in their EHR, electronic health record, and so on. So this is really, if you think of developing data science, this is in a hospital setting, especially in critical care, this is the setting that one would like to start because it's data rich. Now, why critical care space and why are we focused on that? Well, cancer has its cancer centers and cancer research. Cardiovascular centers, similarly as American Heart Association and lots of different research thrusts that happen throughout the country. Critical care, turns out, does not have that sort of strong research base as such. A variety of reasons why this is not there, but primarily, if you think of critical care being such a wide aspect of healthcare today, it turns out almost in all hospitals, up to 40% of the costs come from critical care space. So it's more than what you would think of the other centers are providing in terms of cardiovascular center, cancer center, and so on and so forth. So critical care actually is a very expensive situation for the hospitals. They need to make sure that this is where it's lean and mean in terms of being able to help patients in the best way possible. Now, critical care space also has certain unique challenges that are not similar when it comes to other centers. So for example, if you have a diabetes patient who goes to a doctor fairly regularly, the doctor then gets to see the progression of the disease or improvement of the disease over a period of time. Usually it's months to years or up to the lifetime of the patient. In critical care space, though, they don't have control over that. They receive anyone who comes through their door, and they have to know how to treat them, irrespective of whether they came in for burns, cardiac issues, they came in for a traumatic brain injury, or what have you. So the specialty required here is a mix. And so the doctors here typically tend to know a lot about everything, and that also overburdens them when it comes to the amount of data that you start providing them, trying to help them in their diagnosis process. And confounding all of those already existing issues within the critical care space is the pathophysiology of the human body. Now, as an engineer and as a data scientist, I would love to think of everything as data input. You have a black box in between that does the number crunching, and then there's a data output. Now, even if the box, if I understand it or not, I would love to assume as an engineer that there's some sort of a correlation between an input and an output. There's a direct handoff in some sense which I can start tracing back at and relying upon. But in the human body, that's absolutely not true. In fact, if you touch any part of the organ system, it affects another and the other and so on and so forth. And if you neglect any, again, the problems manifest across the body. So in the critical care space, they're literally looking at all the organs, all the issues that perhaps could happen, all the worst case scenarios they have to think of. And especially when continuous monitoring in ICU settings where data is rich, they have so much data that they're seeing, they still have to think about all these other issues that might manifest over a period of time if they don't notice it early enough. And it constantly happens that they miss it because of the complex nature of the human body. So this is where really what we are trying to do in the research center is, especially in the data science core, is try and take data, develop analytics, and see how well we can actually help in the decision-making process, especially because the decision-making process tends to be time-bound because of the nature of how they receive these patients, as well as complex because of the multi-organ issues that they typically tend to see in these patients. So in that decision-making process, what happens is there's a lot of variability because of those complexities. So we want to reduce that. And in addition to that, we also want to be able to detect certain things, especially overt events, well before it happens. Currently, especially in ICUs, you have, it's called intensive care unit for a reason. You have doctors and nurses constantly vigilant on the patient. But despite all those efforts, there's always surprises. Doctors come in, make sure the patient's okay, everything is noted down in the charts as okay, they walk out, 15 minutes to 20 minutes later, they get paged with a code call, with an emergency call saying, please come, your patient has just collapsed. This is a constant feature. I've lived in this space for some time now, and I've seen that this happens to be a constant issue for physicians and nurses. Things really change unexpectedly. At least with adult bodies, you tend to see a gradual change in certain cases, but pediatric cases is even more difficult to predict. The young human body is capable of compensating very, really well. And so because of that, all the vitals, all the measurements that they're trying to capture, the human body is faking it to a point where it cannot anymore, and all of a sudden the kids crash. And so this space happens to be one of those where we thought, okay, if that's the case, let's see what we can do with data and analytics to try and solve that. And of course, in doing all this, we hope to have improved outcomes for those patients. Now, as a data scientist, the first thing I want to understand is what's the data look like within the healthcare space, especially within this critical care space. Now, we've all experienced this, I'm sure, in some format or another. We walk into a doctor's office and they ask us certain simple questions. What's your age? They check our weight, so on and so forth. Now, these are static data that they collect, which happens to not change very often, which happens to be once in a while they need it, and in many cases it doesn't change at all. And so they just need that point of reference, and that's good for them. But then there are certain things like your heart rate, your blood pressure, and so on. So every time we go in, they tend to check that over and over again. That tries to give them a little more sort of a trending information of whether things have been changing or not. Now, this happens to be a blood pressure from an ICU person. So any of us, if we just visit the doctor routinely, it's just one blood pressure check. But in a person in an ICU, they typically tend to do that a lot more. And if you're really sick, it happens once every hour on the hour, just like this. This image right now is showing you those red points are essentially when a nurse walked in and collected the blood pressure for the patient. And it so happened that when they collected that patient once every hour on the hour, collected the data, it happened to be within the blue band, which is considered as the normal, stable band. So the patient, in reality, whenever they measured, looked fine. But if you look at the granular level data of the same patient's blood pressure, there's a huge amount of variations that happens even between those hours. If the physicians and nurses knew this was happening, their reaction would have been a lot different. So this is where I think data collection becomes important within the hospital system. And when we say data collection, now this is a neonatal ICU. This is a simple example of what a neonatal ICU can look like. And I say simple because it can get much more complex than this in many cases. So on that small real estate of the human body right there, they're collecting vast amount of information continuously. So as I said, we're really good at collecting certain information, which are static typically. Things like x-rays, imaging, and so on. You collect it once, you're able to store it, well and good. Things like lab records, their blood labs and so on and so forth, that's also collected quite efficiently and stored whenever it's collected, it's not lost. But then on the top right over there, you can see things like the waveforms, ECG, ABP, and so on. Arterial blood pressure, ABP. So it's an invasive line that they put in and they measure your blood pressure continuously rather than blowing up a cuff and then being able to measure it once in a while. Now those measures are being collected from these patients. But the problem is they're not storing it. So the only way that data is being used right now is if a nurse or a physician walks into that room, stares at all the monitors for a bit, assimilates all the data that they need, puts that together in their brain, and then decide, okay, this is how my patient is doing right now, and also predict how their patient will be doing in the near future. So that's the only way they can use that data at the moment. And this is not just in our hospital. This happens to be a commonality almost across all the hospitals across the globe. And so why are they not collecting that data? Waveform data happens to be extremely rich data, but it comes in at a speed that is typically not conducive for storage, quick and easy storage. So a single lead of EKG, you can have up to 12 leads of EKG, which is the electrocardiograph. A single lead comes in at 240 samples per second, 240 hertz. And that's on a typical system. It can vary plus or minus 100 hertz, but that's a lot of data from a single lead. And really sick patients have 12 different leads. And that's just one source of ECG data or EKG data. Next you have the arterial line, then you have EEG and so on and so forth. So quickly you realize how much of data starts coming through. Now even from the physician's point of view, the nurse's point of view, that's a lot of data for them to even read. So they walk in, they're typically looking at their favorite monitors. They're not really looking at all this data, but it's being collected, or I should say measured, never stored though. So that's a big problem. Now, if you look at what data collection typically looks like in the healthcare space, you have a typical stockbroker, medium-sized stockbroker office. They tend to collect 1 terabyte of data on their stocks and their clients. 1 terabyte of data. Now, if you look at Boeing 747 flight, domestic flight, it tends to be about half a terabyte of data per flight. All the engine parameters and so on and so forth, weather patterns, what have you. Take a patient's case here. In the best of the hospitals, it's a fraction of a terabyte. Now, if they happen to capture certain images, image modalities such as CT scans and X-rays, that number tends to be a little bloated, but on average, it's just a fraction. And whatever they capture is just giving them a snapshot of the now. It doesn't help them in predicting what's going to happen in the future. So we have clearly seen how data can be helpful in clinical decision making. So for example, if you just had a patient sitting in the room, the doctor had no idea about any sort of data elements for this patient, and they could just visually look at the patient and decide what had to happen. They would walk in, they would look at the patient and say, okay, this person looks a little flushed, maybe red in the face. Take a nap, I'll come back half an hour later and see if you're still doing the same or better. That's pretty much what they have in terms of how they can help at this point. But you go take one step further, then you start collecting data, things like, so it's going to be column B. You'll have things like heart rate, blood pressure, systolic, and so on and so forth, SpO2. Now, all of a sudden, you're gathering a more comprehensive internal information about this patient. This gives you a better idea of what's happening to the patients. The next step from there, column C, is essentially being able to use that data in a more intelligent fashion, rather than just using it as raw bits and bytes, raw numbers. How can we use that in a more comprehensive or an aggregate manner? And so there are these scores, very well understood, clinically validated scores that exist. So if you give 30 different vital signs from column B to a physician, they need to really comprehend what those 30 really mean together. But if you give them C, they're now able to get one score out of all these being put together in different formats. And all of a sudden, they know what they're looking at, they see these values that make sense to them, and the score is kind of helping them adjudicate their own decision-making process. So it seems to help a lot more. If you go further down the data chain, if you add more data to it, it's all these monitors that we are missing data from. The data, if it's not seen by the visual eye, vaporized. So why is that important? So each of these data, so for example, I go back to the ECG, a single lead of EKG is enough for an electrophysiologist to be able to tell whether the left side of the heart is stronger than the right, and so on and so forth. Very detailed information of a single organ. They're able to recreate a picture of what's happening inside during that snapshot of when they collect their data. And so basically that's being used right now for such things, for spot check and very precise, very focused checks of what's happening to the patient. But in a comprehensive manner, nobody can use it, simply because of the rate of data and the inundation of data that happens to them when they walk into an ICU room. So column E is really where my team and I want to be, and we are. We are trying to use all the data from all the other columns, combine that together in an intelligent fashion, so that at the end of the day, we can give the physicians a score or a couple of scores, which really helps them bolster confidence when it comes to their own decision making. We're not making the decisions for them, we're helping them make the decisions. And that's where I think the future of healthcare really needs to be, and is luckily headed that way. But there are many, many difficult steps that needs to be taken to get there. So because of all the issues there and the reasons we wanted to collect this data, so we formed a small team and decided, okay, let's see how we can get that going. So what you see here is the small team, and as I told you, Mark is the better looking one between the two of us. Well, so be it. So we started collecting, we wanted to collect data. We walked into the ICUs and saw what the system looks like, what the infrastructure looks like, and we thought, okay, this should be relatively easy. 4 years and $3 million later, this happened. So we built a completely different infrastructure within the hospital system. And so this infrastructure was developed purely for the purposes of being able to not only just collect the data, but also be utilizing it later on for research purposes of developing intelligent analytics, predictive analytics. So what you have on one side, the green side over there, is the live or real-time data. We are now able to capture these waveforms, not only from the monitors, but actually show them on the phones and iPads and whichever screen you want to choose to look at this patient from. So that real-time component has been established. Along with that, we are able to deploy our analytics, tested and validated analytics, in this real-time component. So it's consistently consuming this real-time feed of data that's coming through from the monitors in the electronic health record of these patients. Now, once we capture that, we also de-identify and store every single bit of it. So we are storing vast amounts of data. For the last 2 years that we've been live storing data, we've collected about 75,000 patients worth of data. Every single bit that we can get from them, we're capturing it. And that's really useful for someone like me, because I then get to go back and dig through data and try and see how many different types of analytics I can develop. But having data in that format, being able to store it, is not sufficient. Someone like me, I'd be okay going through Hadoop and SQL and MongoDB, what have you, trying to understand how to fetch this data from different places, because all data does not sit together in one single place. And so, but so for someone like a physician who's helping me develop these analytics, who's giving me his clinical gestalt while developing these analytics, it becomes a lot more complex for them to actually access this data just because we were able to store it. So we've had to develop a set of tools that enables us to do this in a much, much easier fashion. It's almost like click and play fashion. And that has helped us really speed up the process of developing these analytics. So just to give you a recap on how we have set this all about, right? So we have Michigan. We have now collected we have not set up the ability to collect data, which is fantastic. We're also able to harmonize it. So typically when we do research or any sort of product development, you have these cycles. You have these very fixed time points in which you know you've achieved something and move to the next and move to the next and so on. It's no different with analytics in medicine. We have data, we have to bring the data together, we harmonize it, that way all the different disparate data sources are talking together and happy with each other. But then, since we are in the medical field, we need clinicians to be able to view this data, as I was saying. We need them to annotate regions of interest, to go into that data, to be able to view it in such a way that they can tell us regions of where patients were doing okay, not okay, and crashing. So to be able to provide that, we had to develop our own system. Now, again, for the data scientists, maybe that view is not good enough. It's a dumbed down view in their opinion. So for the data scientists, it had to be provided in a fashion where they can consume it in MATLAB, Python, or any other language of their choice. So the same data, which has come from the monitors and the EHR, has to now feed to two different sets of people, at least, if not more. And once you have done that, you're actually able to develop a clinical decision support system. Now you have the clinical gestalt, their opinions of what they see from a physician's point of view about the patient. You have data scientists who are clinically zero knowledgeable, yet they're able to use this knowledge that the physicians give them, combine the two together to get a clinical decision support system. But that's not where it ends. So once you have a clinical decision support system, which has been developed in retrospective data and so on and so forth, you need to see if it works with new patients. Most analytics fail when it hits the first set of new data that it sees. And it's no different here. So we've had to develop a platform to be able to deploy these live, these are clinical decision support systems, be able to get feedback live from the physicians who are actually seeing this as they treat the patient, and then go back to the drawing board and change a few things and reiterate and iterate and iterate. It's a constant process. If there is a lack of fundamental infrastructure to enable us to do this over and over again, we would take years to develop even a single analytics. Having developed all of this, we are now confident in the fact that we're able to develop multiple at the same time. The runway has shortened dramatically for us. So now we've collected all this data, right? And what does the data look like for us? It looks like that. It's brilliant, right? But it's blurry around the edges. It's noisy. I don't know where to begin, where to end. And it's a difficult process with this data, right? So as a data scientist, though, it's exciting because I then get to dig through this data on behalf of the clinicians, behalf of the patients, and then try and find something beautiful inside it. Try and recognize something that I can give as an insight to the physicians so that they can then take it and apply it during the path of care. And this hopefully will help better patient outcome. But as I said, data that we have is noisy. I mean, medical data is noisy. So, and I'm sure most other cases are. So what you're seeing is a single example of an ECG or an EKG. A small window of, I think, about 10 seconds. On the top right, you have the blue or the green color box. That's what a typical ECG looks like, as shown on TV, sort of ECG, right? Literally, in the movies, that's how it looks. But in reality, the red boxes are what we're getting. It has a tremendous amount of noise inherent in the data. If a patient coughs, if a patient moves, it adds to it. And so just imagine an analytic that is consuming this data now also needs to know what is good data and bad data, live as it's consuming it. There is a phenomenon because of this called the alarm fatigue. I don't know if you guys have heard about it. It's been in the news as well, apart from academic journals. It's essentially where nurses and physicians are they have just tuned out when it comes to alarms. They walk by a patient, they walk by these alarms, cacophony of alarms going off, beep, 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 and they don't react. It's not their fault, it's just that they've tuned it out. For ages, they've been hearing these alarms. So why do these alarms go off and why don't they react to it? Because these alarms are almost always bad. unless someone's taken the time to set it up correctly to make sure. Even then, it gives false alarms. And so the amount of false alarms they see because of these monitors are tremendous. They've also got given the mute button, which tends to be dangerous too. So these nurses or doctors go and mute it. 15 minutes later, they get a call saying the patient has crashed. That's because of this kind of data. There's really nobody you can blame. The data itself is bad. And so if you're trying to develop analytics on top of such data, it's going to be worse. So in reality, when we have to start developing something, the foundational part that I started working on was this, to try and see how we can remove noise or salvage areas of noise. So here we have data coming in from the monitors. We are able to capture it now. And in real time, we have deployed analytics that captures noise. It's able to recognize signal-to-noise ratio in a variety of different domains, extract the noise where it's salvageable, remove it, throw it, and then only use the data as is once it's cleaned. Or if it's to a point where you cannot salvage this data, discard it. So that way the analytics never sees bad data. And only then can you have good analytics that's going to help in the clinical decision-making process. So the foundational aspect of our work actually was in the noise removal process, trying to recognize bad data. This is where we started. Usually in my previous work, I would start with the endpoint of trying to save lives in the most honorable manner, and then realize noise was the biggest impedance factor for me to get there. In this case, because we started from the ground up, given the infrastructure, we were also able to think of this in a very rational manner of what are the first biggest problems that we're going to see before we get to the point where we start saving lives. So this is a simple, quick example of, if I can get to play this, there we go. So this is a quick example of Analytic running live, trying to recognize noise on a very noisy ECG signal, or a very typical ECG signal. So all the green dots is where it likes that portion of the signal. The red one is where it thinks, maybe, maybe not, it's salvageable, and so it's deciding on live whether it should salvage it or not. And the ones where it's not put any dots, it's basically saying, I don't want to use that region. So this is just a quick example of a real-time decision support system, but at its foundational level where the physicians never get to see this. This is not designed for the physicians, this is purely from the data science perspective. So once we did that, we then started looking at what are the use cases that we can really target. In a way, if we look back, we've really developed this for the masses when it comes to the platform. We intend a lot of different physicians to use it. We intend a lot of different research scientists to use it. We also intend a lot of PhD and master's students to also use it. But in reality, that was never the aim. We happened to have developed something that is usable by many others. Our aim was to really focus on certain end game scenarios that we really wanted to solve, some problems that physicians face or are having trouble treating their patients. And so these are our focus areas right now. We've, of course, expanding on it as we improve on each of these. We want to add more. But right now, these have, for the last few years, been our focus areas. So traumatic brain injury, which happens to be really complex in being able to monitor and decide where this patient is headed. Hemodynamic instability, things that really shock patients or physicians today is actually that, because patients look fine, all of a sudden they're unstable and they're crashing. ARDS, or acute respiratory distress syndrome, again, one of those very common, but extremely expensive, and not just from a cash perspective, but also from the life perspective. And sepsis. Sepsis is a silent killer in some sense. So when you see these reports on death discharges of all these patients, typically you read things like, okay, polytrauma because of a car accident, or you read all these other traumatic brain injury, or stroke in the brain, and so on and so forth. But in reality, they would have died because they would have gotten septic, which is essentially a multi-organ failure, that would have led to death. So this is like all roads lead to death in some sense, hemodynamic instability and sepsis. But they're never a billing code. Nobody bills because of those things, but they're the underlying disease factor that leads to a billing code such as cardiac arrest. Excuse me. So everything that we've been developing in all those fronts and those focus areas, we have been also very cognizant of the fact that this is not just for the University of Michigan. University of Michigan is an ivory tower of medicine. It's a premier, world-renowned institution. Any patient who comes there is actually lucky because they have some of the best people working on them, as well as some of the best resources thrown at them. But most of medicine is practiced, almost 99% of medicine is practiced outside of such centers in community hospitals. The same number of cases, the same number of issues and drastic cases community hospitals sees. They get overwhelmed and then they get transported to places like University of Michigan for much higher acuity care. So these community hospitals are really where we want to make sure benefit from what we're developing. So that's from the analytics perspective, right? When you take the infrastructure level, really the infrastructure level is only required at a place like University of Michigan, not these community hospitals. The way we've, going forward, the way we've already planned things and we're executing things is a lean instance of what we're developing. Just a premise of these analytics lives inside these community hospitals. Very, very little cost to entry. Just get in there with the leanest premise servers, and then we are able to capture all that data. So we've designed our next generation of the infrastructure to be able to do that. So that way we're able to scale it to a variety of hospitals. And one of the ways we're doing that, in fact, the chief way we're doing that is through the cloud. So we are orchestrating a crowd infrastructure right now where we're, as we speak, transporting everything that we have in our on-premise site to the cloud. So that way we have these lean installations in all these community hospitals across the US. Coming back to where I was talking about, every project has a particular set of path, and data science is no different. So you have the aspect of looking for data, finding cohorts of data. And then once you have found that, you have to visualize it and really dig through it and explore that data, understand the data. Once you've done that, finally you get to build your analytics, right? So these are commonalities of phases. So we, as I mentioned before, we have certain tools to help get there. This is a simple view of our dashboard where we can start clicking on the tools of choice that we want. The first tool is called Cousteau. This is a tool which is essentially used for finding cohorts. So as I said, we have 75,000 plus patients worth of data. Not all of them are going to be useful when I'm trying to look at sepsis or I'm trying to look at traumatic brain injury. So how do I find patients who have had that? And plus, within that, a cohort of patients who went through a certain episode of interest, which was unnoticed, which was always a surprise for the physicians and so on. So this tool is really that simple, abstracted layer of digging through data. Physicians love this. Physicians have been using this at UFM. Essentially, they get to really throw questions at it. It's SQL on demand, if you can think of it, just by clicking buttons. So they can ask, show me all the patients since, I don't know, January 1st, 2016, who have had their blood pressure, or mean arterial pressure, go down below, let's say, I think I've put in 70 there, 70, 60, what have you. So this is a case where, patients likely on the downward trend. And so it's important now to see how quickly I can get back. Before this, there was no mechanism for us to be able to gather all this data. But through this, we're able to do it much easier. And this, once they click all those parameters and click OK, the data comes back to us almost instantly, within a few seconds. So we've really optimized our infrastructure to be able to do that. Now, once you've created the cohort, you need to visualize it. This is where physicians get a visual view of the data outside of the monitors that they're typically used to seeing it in, and it then vanishes. So now they're able to re-see that data which has vanished, along with time-aligned time points like medications and so on that happen. So it helps recreate a storyline of what happened to this patient. And then they're able to annotate that data for us. Stable, unstable, crashing, so on and so forth. These annotations are extremely important because what we're developing is predictive models. And we want to make sure it meets the standards of what physicians think are okay and not okay. So this is one of our projects for traumatic brain injury. I'm just going to give you a brief demo of it really quickly here. Traumatic brain injury is, again, one of those cases where physicians would love to see inside the brain, but they cannot. Right? So they're trying to constantly guess what's happening. Now, we call this battle eye, and there's a reason behind that. It so happens that there's a fish called the Pacific battle eye with a transparent head. So you can actually see the brain. And so we were trying to see if we can develop analytics that allows physicians to see inside the head, traumatic brain injury patients. And that's why we called it battle eye. So this is how it looks right now. So this is how it looks right now. This is the dashboard that the physicians get to see. It's analytics, many different analytics running together. The bottom three rows over here essentially are scores, indices, which are giving diagnostic measures. So it's telling you what's happening to the patient now. It's giving a snapshot of, okay, right now, they're okay, they're not okay, and so on and so forth. The top two are predictive. They're trying to tell how the patient will be doing in the future. So these two are novel. These two are novel things that we've developed in-house. These, however, are very well cited, very well known by the physicians. They love using this all the time, but they've never had the capability of doing it because some of these require mental math, which is easy enough, but then there are a couple of them which you cannot do just by mental math. You need to know, you need to have some computer system running, processing this data to be able to see how the patient is doing with those scores. But anyway, I'm going to quickly play this video here. This is of an actual traumatic brain injury patient from our University of Michigan hospital system. And you'll see that because of the frequency of data we're getting, we get to choose how often we need to present a new score. In our case, we are presenting it once every 30 seconds in this. We can go down to up to 2 seconds. So once every 30 seconds, there's a new data point that's being generated. I'm going to forward this a bit. As you can see, all of this saying that the patient is stable, green, whereas these two, from the very beginning of this video, you would have noticed they were saying red. This patient in the future is not going to be doing well. So it's predicting that the patient's going to. So as the time progresses, you'll notice that some of the indices start turning red. And these two have still consistently said, nope, this patient is not going to be doing well in the future. And a little, time keeps going by. I've sped it up, of course. As time goes by, you'll start seeing these spikes where the human body compensates, decompensates, compensates, decompensates. This is essentially where the human body in itself has a response. So without medication, without anything, the body already knows what to do to an extent. So it's trying to do that, trying to correct what's wrong. But then at some point it gives up. The compensatory mechanism fails. And so they go really into the red. But these two predictive algorithms consistently were saying, nope, something's going to go wrong in the future. And in this particular case, it went on to a point where a code call was called. So drastic intervention, patient was rushed into surgery for correction. So the two analytic, the predictive analytics up on top, were able to predict a little over an hour before the incident. Now you might think this is not much, but in the case of critical care, an hour can be a tremendous amount of time. This particular physician who treated this patient, of course, he didn't get to see our analytics while we were doing this retrospectively, blinded to him. But when we showed this case to him and said, look, we could have figured this out a little earlier, 1 hour earlier, he said, if I had known this 15 minutes before we actually ended up intervening, I could have done much less. I didn't have to do all these other interventions to save this patient. So this is just one of those cases where we realized we were onto something. And we did a lot more such cases, and we're building the cohort. Of course, these cases take a long time because we go through clinical validation, adjudication with several different physicians and so on. And our average time for detecting before these overt events has been about 15 hours, 14.9 hours. So 14.9 hours before a drastic intervention called RRT, Rapid Response Team, descends on this patient, our analytic has been saying something's going to go wrong with this patient. So this has been extremely encouraging. Like I said, this is just one of our analytics. We have more. But this is one that has progressed the most. So all this while, I showed you glimpses of what signal processing would look like with such data, trying to bring the data together and so on. One of the key components of being able to develop a predictive model is machine learning. And in our case, of course, there are several different types of machine learning that we can use. But since we have the luxury of sitting beside physicians and understanding what they see every day, we, of course, chose supervised machine learning. So we have their gestalt, their labels given to us, and then we train the model to understand what they're seeing. So it's really taking their years of experience and converting it to math, and that's what we do in terms of machine learning model. And so this is just a quick glimpse of our pipeline of how we develop usually with analytics, signal processing, machine learning, and so on and so forth. But machine learning, highlighted in yellow here, happens to be the most time-consuming aspect. Getting till here is all well and good. It's fun. It was fun. But machine learning, as soon as I got there, I realized it's taking me months to get really completed. And so to give you an example here, there was an analytic we were developing. I wrote the machine learning code from scratch in Python and MATLAB and so on, all the libraries, free libraries I could get. I optimized it. I was able to develop one good model with it. And it took me about a month, 2 months, to develop this one decent model, which then I presented to the physician. Physician gave me certain suggestions and said, it doesn't work here, it doesn't work there. I had to go back and restart that process. And again, now I have the multiple combinations that I can start with again. It's millions and millions of iterations before I get this one beautiful model. So then the problem becomes, how do I improve this? So because we are a small team, we've had to work smart from the beginning. We work hard, of course, but that's not been enough. So we've had to see, how can we make ourselves more efficient in certain areas, right? To give credit to University of Michigan, we are a small team, 100% focused on this all our time. But the resources of University of Michigan are at our disposal. So we are able to do this because of that. But our core team, the 3 of us, have just focused on this and trying to improve this process. So this is taking 2 months. How can we reduce this? We've reduced everything else. Why not this? So we ended up using DataRobot as a product. I guess DataRobot is presenting right after this in one of the rooms. Essentially what it ended up doing was going from 2 months to 6 days. Much simpler for us. So it was a rapid decrease in terms of our iterative timeline. Not only that, I was able to develop really hundreds of models at this point in those 6 days, rather than end up with just one model at the end of the day, end of 2 months. So this was really useful for us, and one of those areas where we had to work smart, so we started using tools that are already available. So in conclusion, I just want to, these are not novel in any sense. These are cliched, in fact. But these are absolutely true. For the last decade that I've been working with implementation of these decision support systems and so on, and developing them from scratch. So I was a research scientist. I then became a person who saw the translational side, from research side all the way to the bedside. And so seeing all of that, these 4 things are something that always makes sense, right? To give you a quick example, ED physician reached out to me with data from hundreds of patients saying, this is the data you get within the first 6 hours of a patient walking into our ED room, our emergency department. This is all you get. Using this data, can you predict whether they're going to die? Seems simple enough. So I took that data, worked on it, few weeks later, got back to him saying, I'm able to predict their death 98% of the time. Now, of course, he was skeptic. More than him, I was skeptic. I've done machine learning long enough to know that 98 does not make sense. So I told him, let's just sit together. I want you to explain to me what's going on here. Domain knowledge is critical, right? I lacked it. He's the one who has it. So we really sat together and dug through the data. Amongst all the data, some of these are lab values. So you have hemoglobin content and creatinine and blah, 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 blah. In between, there was a value called DOD, and then so on and so forth. So that, it looks like, was leaking. And turns out DOD stood for date of death. And so whenever that column was filled, I was predicting perfectly. Actually, not perfectly. 2% of the time I was missing it. I don't know how. But you get my point. It's really easy to think that what you're doing is fine, right? And assume that 98% is beautiful. This is how the world works. In reality, it doesn't. You have to do this 100 million times before you realize, okay, now I know how not to do it. So anyway, don't confuse yourself when it comes to data. If you have more data, it doesn't necessarily mean you have an insight out of it. Don't confuse insight with value. Guilty as charged. So I looked at a column which I didn't know what it meant and thought it was the most indicative column when it comes to the outcomes. Don't assume you can interpret data. Again, guilty as charged. And finally, don't underestimate the challenge of implementation. I can't impress upon you how important that is. For years, I've developed analytics on my desktop, right? I view servers, all retrospective data. The first time we started looking at real patient life, lots of things had to change. Lots of things had to change. Mathematics that works on retrospective data does not necessarily work on real-time data. The same data, but the math is different. So these are things that you'll have to be cognizant of before you think, okay, I'm going to implement this, it's working, I'm going to implement. It doesn't work that way. All right, thank you so much. Thanks a lot. Yeah. Right, great question. HIPAA is absolutely the core of the data collection that we do. Our entire system is designed in such a way that it's HIPAA compliant, and we've got certified internally to make sure we're HIPAA compliant. In the real-time part of things, the only person seeing this are the physicians and the caregivers, and they're okay seeing the identified data. Retrospective, I couldn't get into the details, but one of the boxes in the architecture diagram is the de-identification process. We call that the cognito. So essentially, it de-identifies based on HIPAA regulations and then stores that data for retrospective use. And only a few of us know how to get the key back to be able to. So the physicians, whenever they ask, we're able to provide the key back to that. Yeah. Right. You're absolutely right. And physicians' time is inordinately, they're really busy. If we thought we're all busy, they tend to, and University of Michigan physicians are overachievers. They not only have clinical duties, but they're teaching, they run research centers, and they have MD and PhDs. So these guys do a lot. And so to be able to capture their time, it was difficult in the beginning. But luckily for us, I'm embedded inside the hospital system. I'm a faculty inside the hospital system. So I have access like no other when it comes to these physicians, first and foremost. Secondly, I was able to sell them on this idea of data analytics. Many of them were skeptics. Many of them were actually excited to see something in the realm of data analytics helping them. And so given this mix of crowd, I was able to convince all of them that there is something we can do. Let me show you examples, blah, blah, blah. And once they saw the light at the end of the tunnel, so to speak, they were all on board. And so they dedicated weekends for us. I would sit on Saturdays and Sundays with them, actually looking over patient data and trying to get this annotation. It's really expensive process, and I was lucky in that sense. All right, great. Thank you so much. Thanks for sitting through the whole thing. Appreciate it.